Hello everyone. In today's notes we're taking a look at the Pythagorean Theorem. Previously we were looking at reducing radicals, simplifying radicals. And some of these problems will have us leave the answer in simplified radical form. Other problems will leave it in a decimal form. So we'll just pay attention to the directions on each of these problems. Many of you have seen this Pythagorean Theorem formula before. It's nothing new, but we are reviewing it because it comes up from time to time in semester 1, but we're going to come back to it in much more detail in semester 2. So you'll be seeing it twice, really. So let's take a look at the box here, and this outlines the wording and the diagram. You can see we lost the top part of that triangle in this page, so just go ahead and fill that in so we have a complete triangle. So first of all, we must have a right triangle. Again, that little box tells us we have a right angle. That means the triangle is a right triangle. If it's not a right triangle, the formula does not work. Here we have three sides. Two of the sides we describe as being the legs of the triangle. So what you see here with the A and the B, those are the sides that are touching the right angle. Those are the legs. And then opposite the right angle is the longest side that we call the hypotenuse. We spell that hypotenuse. So there it is. And so the longest side is assigned the letter C, so that we can always know that whenever we come across the letter C, it's talking about the longest side of the triangle. Now, traditionally, you are more used to seeing the formula presented in this alphabetical order, where we have a squared plus b squared equals c squared. If we have an equation, we can exchange the sides around. So it doesn't really matter if the c squared is on the right or if the c squared is on the left. I'm going to use this where the c squared is on the left, though technically you could do it either way. It doesn't really matter. But the reason why I will do it this way, and why the book does it this way as well, is mainly for when we get into semester 2 and we start working with this idea in reverse. If we take this theorem and we go backwards, we call it the converse. We'll talk more about that in a future section. And when we then take this idea and work it backwards, it'll be easier for some of the problems we do to organize our work with the c squared on the left. There's an awful lot of description here just to communicate what looks to be a very simple formula, but the key phrase that I want to point out is that it has to be in a right triangle for the formula to work. So let's jump into our examples. Here's example 1. It says find the length of the hypotenuse of the right triangle. Now it does not say whether to leave it in simplified radical form or decimal form. So let's go ahead and set it up and see what we get. First, find your right angle. Second, find the longest side, which is opposite the right angle. That's the hypotenuse, and that's what we assign as the letter C. The two other sides are the legs, and it does not matter which is the A or which is the B, but just organizing your diagram this way will then help us get started. So c squared equals a squared plus b squared. My c is the variable. They're calling it x. I'll go ahead and use x in place of c. In place of a, we have 24, so there's 24 squared. And in place of b, we have the 7. So with some of these bigger numbers, you'll want a calculator. And that's what I'm doing here. 24 squared. I take a look at my calculator. I get 576. 7 squared is 49. We'll add those together because they are like terms. We get 625. So to isolate the variable, we have to get rid of that power of 2. We will undo that by taking the square root of both sides. And that's a really big number. I might not know off the top of my head if that has any factors that are perfect squares. So I'll first just type this in my calculator to see if it is already a perfect square or if it will give me a decimal answer. And it turns out to be a perfect square. Square root of 625 gives me exactly 25. So that is the simplified radical form, meaning it's simplified completely. Here in example 2, we have almost a 3D sketch with this diagram, and here's the little triangle that we're working with. In this description, we have a 6-foot board that is resting under the doorknob. So it's forming the brace to the door. And the base of the board is 5 feet away from the bottom of the door. So here's the bottom of the door, there's the end of the board, and there's the 5-foot span. So approximately how high above the ground is the doorknob, and you can see here we have x feet, that's the variable, so this represents the height. If it helps, you can redraw this triangle so that it's just in a 2-dimensional diagram as opposed to this 3-dimensional picture. The bottom is the 5 feet, there's the right angle, the height is what we don't know, that's the variable of x, and then the board length is 6. Alright. Opposite the right angle is the longest side. That's the hypotenuse. That will be our C. The 2 legs, doesn't matter which is A or which is B. I'm just labeling them, and then we'll get this set up. C squared equals A squared plus B squared. In place of C, I use 6. So there's my 6 squared. In place of A, I have 5. And in place of B, that's my unknown. So it looks like 6 squared equals 5 squared plus x squared. Let's square each of these terms. 6 squared gives me 36. 5 squared gives me 25. I want to isolate the variable, so let's move all the constant terms to the left-hand side. And 36 take away 25 is 11. And so what I have right now is 11 equals x squared. Again, we want to solve for x. It is currently being squared, so we undo that by taking the square root of both sides, and that's how we get x by itself. Now 11 doesn't have any factors, so this is its answer in feet. This is the exact answer if it said leave the answer in simplified radical form, which actually it doesn't. It says approximately. So that's our cue to instead turn it into a decimal. So we would use our calculator to find the decimal value of this root 11, and we're going to 2 decimal places. So I'm looking at my calculator and I get 3.32. And don't forget the units on a story problem like this. So notice the difference between an approximate answer and the exact answer. So in these 2 triangles, we had one example where we were solving for the unknown hypotenuse, and another where we were solving for an unknown side. And those are the 2 basics. So example 3 is really going to push us a lot farther because we have a lot more going on than just solving for an unknown side. They want us to find the entire area. We're going to find the area of a triangle here in just a moment. And so the way it's set up, find the area, you might think, oh, well, this doesn't have to do with the Pythagorean theorem. Well, we don't know that yet. Let's draw our diagram and see what we can come up with. It says we have an isosceles triangle. Later on, we'll do more work with classifying triangles. Isosceles means that we have 2 sides that are the same length. And you can see these are the 2 sides with the same length of 17 meters. The third side is the 16. So let me draw a picture. It's easiest to draw an isosceles triangle where you have symmetry about a vertical line right in the middle, so that the left side and then the right side are the same. So here we have 17 meters on the left side, 17 meters on the right side, and the 16 meters is on the bottom. Now clearly we don't have a right triangle, so it looks like we would not be using the Pythagorean theorem. It only works if we have a right triangle. But if we want to find the area, so let me use this space over here on the right. If I want to find the area of a triangle, you may remember that's 1/2 base times height, or base times height divided by 2. So we have the base, that's good, but the height is missing. the 17 is not the height, that's a slanted edge. So remember that the height must go straight up and down to the base. So if we draw the height of the triangle, that's the right angle that we get. And I'll put h here for height. That's missing. So first we have to solve for the missing height. Once we get the height, we'll use that with the base to solve for the area. So this problem really has two steps. First we have to solve for the missing height, then we can answer the question to find the missing area. To do that, we just want a right triangle. So I'm going to take 1/2 of the original triangle. Doesn't matter if we use the right half or the left half. I'm just going to redraw that so we can look at all the key pieces. So here is the height we're trying to find. There's the right angle. There's the base, which we cut in half, right? The original triangle had a base of 16, but now we're looking at half of that, so we have 8 meters on the bottom. And then this slanted side of 17 meters is now the hypotenuse of my right triangle. So here's the right angle. Opposite that is the hypotenuse. That's what we will sign as the C. And then the other two legs, doesn't matter which is the A or which is the B. So setting up my formula, C squared equals A squared plus B squared. C squared is the 17, so 17 squared equals 8 squared plus the height squared. So again, using my calculator here, 17 squared gives me 289 equals 64 plus h squared. Let's isolate the variable by moving the constant terms to the left-hand side. I'm subtracting 64 from both sides, and I get 225 equals h squared. Take the square root of both sides so that we can get h by itself, and square root of 225 happens to be a perfect square. My calculator will tell me that's 15. So now we have the height. So the height of this triangle is 15 meters. So let's find the area. Area is 1/2 times the base times the height. Now again, the base is the original base of the original triangle. So that's the 16 meters, and the height is the 15 that we found on the previous step. So again, I can use my calculator here to help get me a result, and I get, let's see, I think it's 120. Now this is area, so the units have to be meters squared, and there it is. So in these last two examples, for part A and for part B, again, we are returning back to using the Pythagorean Theorem. There should be some sort of indication that we do have right triangles, and I think this little box got left out. So just add that to your triangle. We have to have right triangles if we're going to use the Pythagorean Theorem. In class, I would say, okay, you try it, find the length of the missing side, and then leave your answer in simplified radical form. So there's really two skills that we're testing for. Can you set up the formula correctly, and can you simplify the radical correctly? So I would suggest you pause this, practice it on your own, try these two, and then when you are set, turn the video back on and finish up to check to see if you got the right answer. For part A, first I find my right angle. Opposite that is the 24, that's the hypotenuse. We assign that the C. The A and the B get set on the other two legs. Let's set up our formula. C squared equals A squared plus B squared. My C again is 24, so 24 squared equals x squared plus 20 squared. I'll use my calculator on these bigger values, so 24 squared gives me 576. 20 squared gives me 400. Let's work to isolate the variable by moving all the constant terms to the left-hand side, and I'm subtracting 400, which gives me 176. So I'm going to now work to simplify the radical. When I take the square root of both sides, I get x equals square root of 176. Now again, I don't know off the top of my head if that's a perfect square or not, So I might first check by plugging that into the calculator, and I discover, uh-oh, that gives me a decimal answer. I can't leave it that way. I have to simplify it. So I need to look for factors that are those perfect squares. So we can guess and check. We could try to divide by 4, or by 9, or by 16, or by 25. Keep guessing and checking until we come up with a factor combination that does not give a decimal answer. So if I check with 4, that actually works right away. If I divide 176 by 4, I get factors of 4 times 44. Alright, let's take the square root of 4. We get 2. But then I have to check to see if I can find still more factors from under my radical. Here I have a root 44, so I know that could be factored into 4 times 11. So we have a 2 on the outside. Here we have the square root of 4, which gives us another 2. And then the square root of 11. So the final answer is 4 root 11. And for part B, again, here is the right angle. So opposite that is the hypotenuse. We assign that in C. Assign the A and the B. And let's set up our formula. I have x squared equals 6 squared plus 12 squared. So x squared equals 36 plus 144. I will combine like terms on the right hand side, and that gives me 180. And then we'll take the square root of both sides, and that gives me, well, the square root of 180, which I need to check for factors. So again, with a big number like that, I use my calculator to guess and check to see, is it divisible by 4? Is it divisible by 9? It turns out that it is divisible by 4. So let's take the square root of 4. We get 2. And then I have 45 under the radical. Don't stop now. Check to see if you have more factors. 45 could be factored into 9 times 5. So we have a 2 on the outside. Take the square root of 9. We get 3. And then we have root 5 in the back. Multiply your coefficients together. We have 6 times root 5. And there's the answer.